Here you can see the proof of lemma 23.2. Okay, so here in the statement they are given you something. So in the first few lines you are writing, you are rewriting what is given in the statement. Okay, so let us write it. So here first I am writing, given the sets C and D form a separation of X. In the statement they are given you like that. So by the definition of separation of X you can write all these. Okay, what you have wrote by definition you will get this. Okay, when you find the union of these two, that should be, you will get a value, right? That value will be equal to this capital X. That is, that value should be equal to our topological space capital X. That is what the first condition of separation of X. And then this C should not be empty and D also should not be empty. And then when you find the intersection of C and D, the value should be empty. Okay, and also this C and D will be open in this capital X. These are the conditions of separation of X, or you can say in the definition of separation of X you will have all these. You are just writing it down. Okay, now in the statement they are also given you Y is a connected subspace of capital X. Okay, you are writing that also. And now you have to prove Y lies entirely within either C or D. Okay, so from this to this you are just rewriting the sentences that you are given, that they are given you in the statement. Am I right? Okay. In the next line what we are doing is, since C and D are open in X. From this line you are writing, okay, since C and D are here open in X, therefore when you find the intersection C intersection Y and D intersection Y, that will be open in Y. Okay, so C and D will be open in X. So when you find the intersection of C intersection Y and D intersection Y, then that will be open in where? Capital Y. Okay, so now you are finding this. You are writing this. This is one of the De Morgan's identity. Okay, you are just writing it down. C intersection, that is you are finding the intersection of these two. Okay, C intersection Y intersection D intersection Y is equal to, this can be written like this. Okay, by a De Morgan's identity. Now you know the value of C intersection D. What is C intersection D? Empty, right? So you are just substituting the value empty, put this intersection and write this Y. And now when you find the intersection of empty and Y, you will get empty, right? It means the value should be present in both empty and Y. We know that in empty set you don't have any values. It means what? The resultant value, the intersection of these two will be also empty. Is that clear? Now you are finding the union of these two. So this can be written like this. Okay, C union D intersection Y. Now you know the value of C union D. What is C union D? X, right? So just substitute the value X intersection Y. So when you find the value of X intersection Y, you will get Y. How? Y is a subspace of what? Capital X, right? So the what will be the common values of X and Y? Y, right? Because here you can see X, here you can see Y. So what the common value of X and Y will be? This, right? Right? The elements present, for example, if you consider 1, 2, 3 are the elements present inside this Y, means these elements also present in X also, right? So when you find X intersection Y, what you will get? Y, right? This value you will get. So that is why you are writing. Now when you find C intersection Y intersection, you are getting empty. When you find the union, you are getting Y. And you also have wrote C intersection Y and D intersection Y are open in Y. So you have wrote the three conditions of separation of Y. Okay, how many conditions? 3 conditions. Only one condition is remaining. What is that? C intersection Y and D intersection Y is non-empty. That is what the only condition. If you say that also if you say that C intersection Y and D intersection Y is non-empty, then what condition you have proved? Separation of Y condition you have proved. Okay, because all by the definition of separation of Y, all the conditions that you can see in the separation of Y definition is getting satisfied. If this also gets satisfied, that is C intersection Y and D intersection Y is non-empty, then separation of Y condition is satisfied. Okay, that is not possible. That should not happen here. Why? In our statement they are given you Y is a connected subspace of X. It is not a separate. There is no any separation. It is connected. So here what you are writing? If C intersection Y and D intersection Y are non-empty, they form a separation of Y. It means all the conditions to say separation of Y is satisfied, will get satisfied. That should not happen. In our statement they are given you Y is connected. It is not a separation. They are not talking about it is Y is separated by some other sets. Right? In the statement they are given you Y is connected. So that is why here, since Y is connected, there does not exist a separation of Y. Okay, because in our statement they are given you Y is connected. Now then what is going to happen? Therefore one of C intersection Y or D intersection Y must be empty. That is, any one of this C intersection Y or D intersection Y will be empty. So here you are going to write C intersection Y. You are rewriting this, rewriting the same sentence like this. Okay, C intersection Y is equal to empty or D intersection Y is equal to empty. So if C intersection Y is equal to empty means what you will get? Y lies entirely within D. Okay. If D intersection Y is equal to empty, what you will get? This Y lies entirely within C. That is what you will get. So this is what we have to prove, right? What we have to prove? Y lies entirely within either C or D. That is what we have to prove. So from this you have proved it. So hence the proof.